Welcome to today's webinar. The topic today is wind load transfer from RWIND 2 to RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today and I will answer your questions. My colleague Andreas Niemeyer will be the presenter today. He's the head of product engineering in our company. Yeah, that means he's the main responsible person for the development of the programs and add-ons. Okay, some words how you can ask questions. Before I do that, I switch off my camera that you can see the full screen. You can click on that question mark above. Then you need to enter your question in that field, press send, and then I will receive your question and I will answer you. Okay, that should be all from my side. I hand over to Andreas Niemeyer. Andreas, it's your turn.
Thank you. Then I take over with the topic wind load transfer from RWIND 2 to RFEM 6. Today I prepared an interesting program for you. I want to show you how you can move models from RFEM to RWIND, of course. And for this I selected some special models and prepared some interesting stuff that you know how to control all these properties and settings for such an analysis. To have a clear program, I divided my presentation into 5 main points. The first is about modeling in RFEM. So here we talk about how or which type of elements you have, what you can transfer, which properties you have, which discretization options you have, how you can control mesh, and so on. In the second point, we transfer the model to RWIND. So for me, point 1 and 2 is always connected, but I show you how you can control all this stuff. In the third point, we perform finally from our models a CFD analysis to see which results the RWIND program with its core outputs and how we can use it later. In the fourth point, we use finally the results from the CFD analysis in RWIND. Let's say we move it back to RFEM for a further static analysis, for example. And finally, I want to sum up everything and give you an outlook about our current development in this field. As you see in these pictures here on the right side, this is a little bit maybe a sequence how we go through the program today. At first we talk about the elements, how you can move it to RWIND, which type, about meshing options. So this should represent this first part, and the second part represents how you or which results you get in RWIND and how you can use it in RFEM. And this brings me now directly to the point where we jump to the program. So we do it in a live demo. You see how it works, and I jump now into RFEM. I prepared here already a state that the program asks me about the model name. Yeah, so that gives this child a name, for example, TT100. Now, of course, this is a typical RFEM model, and RFEM models always lives that you define and begin what you want to do. And this you have to do in these tab add-ons. You see, you can select concrete design, steel design, non-linear material behavior, whatever, many stuff. But we select today, for today's program, only wind simulation. This means we connect the program RFEM to the RWIND program digitally, and how it works I show you later, but we open these options with this check here. Further, I want to do this presentation without connection to any standard, so I deactivate the classification of load cases, and additionally I deactivate the load wizard, what connects the definition of wind diagrams according any standard. So we do it really rough, really mechanical. This means I have in the following tabs no option to define. If all boxes are great, no standard have to define, the box remains empty here on this side. So let's jump into the program. And you receive a typical RFEM environment with the table on the bottom, with the navigator on the left side, with the toolbars on the top, and with the graphic desktop in the middle. And now we directly can start. But before I pick my first nodes and elements, I want to highlight now the mightiness what you get with this option. Yeah. In RFEM, as you know, you have member elements, you have surface elements, you have solid elements, yeah, solids, and all these elements could be connected with properties, only tension, only with yielding, whatever. So you can prescribe these elements for her statical resistance. And now our team made it happen that you can use all these static elements, or let's say structural elements, in a wind tunnel. So we got a chance to use this structure. Maybe a member is for us as engineers only a line, or a surface is only a surface without thickness, because the thickness we describe by parameter. But this interface to the wind tunnel sees this element not as line, for example, a member, then with this outer hull, so with the cross-section rendering, and moves the hull into the wind tunnel, do calculation, and gives the results back on the line. And this is really a mighty or powerful function. And I want to show you today this function on all type of elements. And I want to start now with the member type first. So let's define a member in the graphics. I pick the member function. Of course, it should be a beam element. Here I define a cross section. So make a new section. Let's start with not the complex section like we just see with an IP. Then let's use a rectangular section. So you see here is our library. On the left part, these blue items are thin wall cross sections like I sections, C sections, T sections, whatever. And on the right side, these gray items are massive cross sections made for timber and concrete. I use now here this squared cross section. Give here a size, for example, 300 millimeters, and assign a material. So for me, steel fits not with this 300 millimeters, so I assign a concrete, and you see you get the expected gray color, and we confirm this setting and pick here the member into the space. Now we get the typical member structure. For us, as I mentioned in background, it's only a line. Here you can imagine the cross section around the line. Of course, we can support it for structure calculation. And if I run, maybe only to give you an imagination what this element means in RFEM, I run a load case self-weight, and here you see the program is doing something, let's say calculating, and now we get the result. Of course, maybe I show you only this wireframe model. You see deflection is really minor because self-weight for this really massive section have no effect. But what we really can see better is, for example, the normal axis force diagram, and you see the normal axis force diagram is increasing to the bottom according to self-weight, and finally this means also a support force on the bottom according to this self-weight with the same size but in the vice versa direction. So statical analysis is more or less working really easy in this structure. You pick the elements, you define boundary conditions, and start calculation, you receive results. But this is not the only work what civil engineers have to do, or also regular engineers have to do in such a program. You also suffered with some topics that you have to consider climatic loads on your structure. And here, of course, we know snow, but also wind, and today is wind the focus. So I want to show you how you can define wind loads on such a structure. Of course, we have standards and rules and articles which gives us schemes for describing wind loads via element loads, maybe about a line load on a structure, but these schemes always related to a specific shape. And because we realized from our users that the shapes always changing, are going more organic or curved, whatever, so you have not always these nice shoebox shapes. Therefore, we started the development of a digital wind tunnel program with RWIND, and we connected our structure calculation of with this wind tunnel program. And here, this allows you to consider all shapes in the wind tunnel, and your entry to this is a load case. So I jump now to the load cases. I open this table row in a dialog by double clicking on the left gray bar. You see load case 2 is already opened. We can give a name, maybe CFD wind. Yeah? And now we have to learn the program what to do. Now we don't want to do a static analysis, and we want to do a wind simulation. This means now, and you get a hint directly because below still the static analysis settings are active. Yeah, because a wind analysis means program is taking the structure, the hull of the structural model into wind tunnel, do CFD analysis, detect forces on the structural model, gives these forces back to RFEM for further static analysis setting, calculates normal axis, force diagrams, bending moment diagrams, calculate deflections, and have so far a two-way calculation, so CFD plus static. So therefore you have to define both here, but we came to this later. Now, what is important for me, you see, if you change to wind simulation, you have here two new tabs. The first is, let's say, the standard description, what should be done behind wind simulation. Here, in the first tab, you have, let's say, I call it simply calculation parameters. If you take a look into, you see, okay, what is behind. You can see, you can check here which simulation type is done, steady flow analysis, so the average time analysis, you get average over the full time segment. You get here a transient flow analysis, where you can calculate over time, where you get for every time step a result. So of course the second option eats more time but gives you a higher quality of result. You can describe the medium what is flowing around the structure. You can define which solver, meshing. You can define options like if turbulence should be considered or not, boundary conditions of the wind tunnel. Generally, the wind tunnel is defined that the bottom is terra surface, that the speed is going to 0, and right, left, and top is slip boundaries that the wind can slip through. You can define if your elements, if the hull surface what you send into the wind tunnel is rough or not. You can define user-defined wind tunnel settings and so on. Further to every setting, maybe to steady flow, you have here your calculation parameters, how many iterations, which turbulence model should be used, which iteration value you monitor during calculation, pressure differences or drag force differences, and advanced calculation parameters. Further, so this is the way how it should be done. Now, what should be done? Because we have a wind tunnel, the question is, what are the load? So in structure model, it's the forces. Here we need a wind speed, what we send in. So you can define here a wind speed diagram over high. Yeah. So you see, it's a typical table. You can describe here, for example, at 0 we have 10 meter per second. At 1 meter we have, for example, also 10 meter per second, and we receive a constant diagram over high. If we want to, let's say, make another diagram, it's also easy. For example, you write here 0.5, here 1, here 10, and you describe here any value. So this table input, this allows you to define any wind what you want, maybe a slow wind, a strong wind, a storm. So the list could be extended. So it's in your hands which wind you send in and which results you receive. In my case, I made it easy, so I make only a constant diagram over high with 10 meter per second and assign it to this load case. In the next, we know now how, we know now what, and in which direction. So if we define here 0 degrees, it means the wind is blowing into X direction, and if you define here any angle, it will be rotated around global C. Yeah. Further, now the description in which region. So we call it wind tunnel. It's a box around structure. Here the beam, what we describe in the graphics, represents the house, represents the beam in the graphics. You see, the wind tunnel is always described according to the maximum sizes, or let's say hull sizes of the model what you place in the wind tunnel, multiplicated that you get also, for example, for high, we know our member is 1 meter long, and here you see the final high is a fracture of this size. No? But all values are great. Yeah, you can't pick it. It's a standard setting that the program automatically detects the size of the wind tunnel around the structure. If I confirm this, you see what happens. According to this 1 meter high beam, the program describes here this wind tunnel box with these dashed lines with the input wind speed in our RFEM. So far, so good. If you want to change this wind tunnel, so no problem, you can do it. You get the mighty to do this. You only have to open the calculation parameters and say, I want to have user-defined wind tunnel options, and now you can describe the values, these fractures roundabout with a factor or with the size. No? In my case now, because I want to explain you how the RWIND interprets the structure model, I make now a really small wind tunnel, not to speak about quality of results and more to speak about discretization. So this has nothing to do with the wind results and more about how the mesh is done. So please see it in this size. So therefore I define here round about 0.5 meter. And to make more or less a 2D problem of it, I describe now no high over above the model. And if I check this, you see our box is really small now, and to see the connection to the structure, if I change this to maybe 0 to 10 centimeters, you see the wind tunnel is going more smaller. So you have the control. You can change it if you want. We have automatism to define a general size according any rule. If you want to change it smaller or bigger, you can do it also. But now I make it really small to show you that you can do it, and go to check meshes and not to wait so long. No? Because if we mesh it, we always have to wait a few seconds. So as small as this domain is, as quick it's going. And now the next point what I want to mention is this is now our structure model, a small member in RFEM, but how the wind tunnel sees this model. Let's take a look. Of course you can press calculate and you see a progress bar and finally you get a result, but when we want to see behind the engine, you can do following. You can double click here load case, go into wind simulation. You have here button to open the wind tunnel program in between, or you have here below results, calculate, sorry, also an option to open the wind tunnel behind. Now, and if you do this, the program is sending the structure model into the wind tunnel program. Now we are in RWIND, and you see, of course, the program has some control mechanism. If we want to turn off simplified model at first, no, I don't want to do this. Later we talk about, so no, and you get, let's say, more or less a similar drawing like in RFEM. Yeah, wind tunnel around this beam segment, input wind speed, navigator, and so on. But we can talk about in the next steps about these options. This is for you now, of course, in a different style, but because it's another program. But let's see how the program interprets this graphic, so this blue box in meshes, how it really will discretized. And for this we go to simulation and say not start, because this small wind tunnel makes no sense, but we only generate mesh to see. Yes, wind tunnel is too small, but we accept this now. And you see program is changing in a mechanism where it shows me what is done. So you have here such a information window that you do block mesh, that you decompose, that you do a snappy hex mesh process, how much elements he already did. So it's more or less informative, and you get the sign when it's ready for your information what he's doing. So generally he moves this rendering graphics from RFEM into this wind tunnel. Here he defines, or he have a really rough mesh, so he describes these blue surfaces by really big triangle surfaces. Then he mesh these triangle surfaces with a, let's say, a finer mesh to discretize the sizes of how fine the mesh is. So he lies a mesh on it. It binds a finer mesh on these surfaces. Later he simplifies it to make it wind proof, and between this simplified mesh and the wind tunnel sides, the program creates a solid mesh where it do the flow calculation, where it detects the pressures, wind velocities, and so on. Now he's ready, and we get the first view on it. Of course, he don't visualize this mesh like a solid, because then we don't see something. So he have always these slices. In our case, because we created it like a 2D problem, we want to take a look at top view. And here for me now is important that you see the program knows that he should be mesh fine near the object. So he creates a fine mesh near the object, and to save calculation time, he increases the size from the object to the wind tunnel side. So here the elements are going bigger. Yeah. So this is the general behavior. The program always wants to mesh near the object fine. But at the moment, nobody said something about how big and how small the elements are. This is done always relative to the model size. Here it's important to you that you know the program knows generally here mesh density, and this mesh density factor is deciding how much elements are globally used, and always with this gradient from small to big. And in this case we have now, let's say, more or less about 350,000 elements with this standard setting. I would say this is connected to a calculation time of 5 to 10 minutes. If you want to change it, of course the calculation time is increased or decreased, but let's change this mesh density to 10%, that you see the change. Yeah? We don't change it here because then we only change it locally and the RFEM don't know it. So every setting we change in RFEM. So I close this program now, don't store. And we say in the calculation parameters, of course, we go into the how it should be analyzed and change here from 20 to 10. Yeah. And yeah, let's check it and jump into the wind tunnel. And you see the same question, no, simplification is okay, no. And if we mesh it again, generate mesh, then I expect that the process is much quicker than before. You see now the global amount is much smaller than before, not about 350,000, and really only a fraction of it. And if we see the splice, we already smell what happened. So let's take a top view. You see, of course, it's fine near object, but the global amount of mesh cells is less. Yeah. So with this mesh density, you changed the global amount of elements what are used, but still the gradient from model to outer sides is used. Yeah. Check what happens. We have now about 60,000. Yeah. Now, you know, mesh density is here for controlling the global amount of mesh elements. Now, of course, the question could come up, how can I control the size of the elements near object? Can I also change it? And yes, you can do. For this, we hold in RWIND the parameter below model, the level of detail parameter. And because this level of detail parameter is more connected to the meshing of the object, we placed this not below calculation settings of the RWIND. Then we placed this in the global meshing of the program of RFEM. And here you have at the end a wind simulation tab where you have a lot of settings, and you see in the first stage level of detail, and here we can say, okay, level of detail should be 1, for example, and we do the same step again. So open RWIND, and of course same question now, and we go to simulate generate mesh. Yes, and I expect that it's running again quicker than before because we changed now the level of detail, we made it more rough. And let's see what happens if we take a top view, and you see now, oh, okay, the mesh is more rough near object, of course still smaller than the rest, but you have with the level of detail your hands on the mesh sizes near object. And this is, I think, really interesting because then you can control the effects what should be calculated near these structures. Now, of course, you can imagine this is now everything what I have to know, and I would say no, this isn't. This is now such a really easy cross section. It could be much more complex, and imagine this is not only a massive cross section than a thin wall cross section. So let's change this section here of this beam from a, let's say, simple shape to a more complex shape, to maybe an AGB 320. And now I change something only to talk about. I define in WinSimulation, hey, please make optimized member topology from 0. Yeah. Why? And only that you know what this parameter means. I confirm it and I jump into RWIND and open it now as before and see, oh my god, I get the same model like before. Is this really true? Yeah? If I generate mesh, maybe I don't see it. Yes, of course. But the program is running, we end up in this, let's say, 30,000 elements as before, and the question could appear, is this a bug or not? And I would say, no, it isn't. You only have to know that there is a function what describes around your AGB a cross section, a rectangular, to simplify this cross section, because for example, if you say for my wind analysis, I don't want to calculate in the detail of cross section sizes and more rough around the structure, then you can simplify it with this function. So you can consider every member like a independent from its cross section shape, like a rectangular cross section. And for this you have a parameter in the mesh settings. Yeah. So let's change it now back to this mesh setting for these sections here, to say, okay, optimize member topology to 5 or 10. In this case it makes no difference, and go back to the wind tunnel and check what happens. And now if you go back to the setting, you see we get this cross section into the wind tunnel if you want, but you can control it by this mesh settings. It's only important that the program knows what to do, what you want to consider. In this, let's say, if you consider only the wind on such one beam, it's clear that you want to do it. But if you have a 50-meter big structure where you say it's covered from something, I don't be interested in this wind analysis around shape, then you can simplify it with this rectangular box. And if we mesh it here with the mesh settings what we had already, then you see the process is that it's fine near the object and it's going bigger to the wind tunnel sides is still active. Of course we have a little bit more elements than before, but you see, our team made it happen that you see your fine near model, but going bigger to the outer boundaries. No? Now, you can see, of course, this is working, but we still get always this question about simplification. And for this, we have really to take a close look what this means. We take maybe in C direction, and you see now, and this could happen a question, why the meshing is not running to the sides of this section. Yeah, so why we have here a small gap. And you can also visualize it like this. So maybe here isotropic, you see the program is binding a mesh around the RFEM model, what is a little bit bigger with some gaps, and this is connected now to the simplification. Of course, the simplification makes sense, not always, it depends, but you should know where you can control it. And for this, we do now a meshing without simplification. So we say mesh setting, wind simulation, and we say here, where is it? The simplification we turn off. This means now the program is meshing directly the exact shape what is coming from RFEM. Okay, we say here calculate open wind, and if we mesh now, simulate, generate mesh, yes, then the program is creating exact the mesh on the blue shape what is coming from RFEM. You see, of course, we have a little bit more elements because you have to consider more boundary conditions. And now a look on the top view shows we have no gaps. Yeah, so maybe in Z direction, no gap is here. Even the mesh on the model is now really exact on this shape. This is okay, but allows you to consider the shapes exactly in the wind tunnel. On the other side, you have a situation not only these nice eye sections, then you also have here, for example, yeah, let's create something like this. So imagine you have more complex sections. For example, we change this section into a user-defined section. So I open it in the editor, in our section editor. So this function allows me to load this current section in our section, what can modify it. So I have it here. Let's say I explode it here, explode, and now maybe increase the stiffness or increase the cross section, generally with a stripe 10 millimeter from steel. So imagine we weld here a sheet, yeah, and you get here such unnice corners, for example. So save and return. So now we have here this section. Okay, and now let's turn on. Here I would not mesh exactly this corner, and here I would say, okay, simplification is okay for me. The size of the simplification decides if we have it more rough or not. So let it with this simplification and calculate wind. And you see, if you change this cross section in RFEM via a member cross section, it's really easy to get this model in the wind tunnel. So this is again really mighty, no? This change, and even the meshing function understands this and can work with this stuff. And to make it better, you have this simplification because you can smooth it a little bit. Yeah. So here only check what happens. This is for me a little bit preparation for the next model I want to show you. But you see, okay, here he realizes no wind can blow in, so it closes the gap, and a top view shows you that he make here, maybe without perspective, that he rounded a little bit, that this corner is not meshed exactly. Now, what happens? This means, okay, no wind can blow in, but imagine we not only have one 10 centimeter beam, then we have more or less a member structure. So if we imagine, for example, we change this beam to 0.5 meter length. Okay, we copy it, maybe here a second beam, and we have something like a corner. So maybe in X 0.5 and minus 0.5. You get something like such a member corner. For us as civil engineers or mechanical engineers, it's only such a wireframe model. For the graphics, it's a really complex stuff and it's intersected to each other. I can look through, yeah. And now the question appears, what happens with such a model? Now I only increase the wind tunnel a little bit. As I wind tunnel, okay, above 0.5, yeah. And yeah, and now we can mesh also this stuff. So let's check what happens with the current settings where we think it's fine. And so let's see, simulation, generate mesh. And you see the simplification is now on. It helps to cover this really intersected geometry, because this is in reality not true, but we try to make it calculatable. And finally you see, and now we have to change, let's say, the view to the surface mesh. The program is binding a simplified mesh around. Yeah, he will cover all this critical situation, but still, of course, you can look through. Yeah, and if you want to avoid that the wind can blow in, you can increase the level of detail. So let's change it and say mesh settings. Level of detail is maybe here, maybe 0. And let's check it again. Open wind. I think the mesh will be pretty rough, because we said now the mesh near structure is bigger. Generate mesh. So size of mesh is really small now, not for real calculation, but it's only for this sense now. And you see, okay, this mesh is more rough because we said this size is bigger, but unfortunately we can still look through. And you see now, only changing level of detail is not helping always to make it wind proof. Yeah, because also the wind can blow now. Of course, with less elements, it makes not really a sense, but the domain don't understand this. So to close it, we added here a further option, and this is now the last option I want to mention in this case. We have also here close openings. And you can say according model size or real size, and say for example 0.1. And if we use this meshing here, open wind and mesh it again, generate mesh, you will see, run yes, that the mesh will be maybe size or amount still rough and small. And now if you show surface mesh, you see the program was able to close this opening. So this is also a really a common question, and this leads me also to the next question, topic. You get with this opening closing function what is available in the mesh option, the option to close these small gaps in your structure, in details, whatever. Yeah, but it's not here to close full structures, maybe a window completely. So it's not made for, it's more for this controlling of this slime or foil what we bind around, if it should close something or not. And now I really lose a lot of words about these meshing options. I hope I could get you a feeling and a value how you can control this meshing. And now this opening stuff leads me to a new type of model I prepared. And I prepared this here, I open it, mixed model. And this is, let's say, I would not say typical model what we receive in our support, but maybe let's watch it first without results in a rendered style. So this is maybe steel structure, I call it hall. Yeah, it's not rectangular and with a banded floor plan, to see how powerful also this 3D calculation is, that you can use also such banded shapes into the structural analysis. Of course, if you calculate it maybe similar like we did it before, You can calculate self-weight. You receive again, if you get defines these cross sections here, it's eye sections mainly with bracings. You receive here deflections in the middle. You receive normal axis force. You see compression on all columns. You see bending moments. You get also, for example, here stresses. In the middle you have this bending, so you have here tension, compression, and finally, of course, support forces on the bottom. So typical general stuff, I would say, in our programs for structural analysis. But now we come again, same story as before for this simple beam. If you want to do climatic analysis, you have to define the wind and snow loads, and for wind we have also this CFD analysis. And here I predefined already a similar load case, maybe only wind load case, one wind scheme in X direction. You see wind tunnel is defined around structure. Here I selected also a constant wind profile over high. And what is now really it could act like a black box if you do this. Press calculate, you get finally deflections. You see super deflection of the structure is going in wind direction, bending moments also fine. So you could use this load case for design. Of course you can do this, but you should always know what you're doing. And here it's really interesting to see inside the wind analysis. And for this, our team programmed now options that you can visualize the wind tunnel results also in RFEM. So you get here wind simulation analysis. You see now this is the wind pressure on the structure. Maybe let's look at first on the wind results around structure. So we have here maybe the pressure scheme. Let's take a look on this view, and you see, okay, this is the pressure around structure, and what is interesting, you get always a pressure peak in front of the column. Here you see maybe the simplified mesh, but this opens for you a situation if you see wind speed that the wind that the steel structure is not covered, the wind is blowing through. Yeah, and this is also the finally what you see from these schemes. This is not what you want to calculate generally, because generally you assume the steel structure is covered by a trapezoid sheeting, insulation panel, whatever, but the program don't know this. And if you see also the only this results here, you see maybe without clipping plane. Yeah, okay, this model is here have some compressions according to the wind, but this is only the grid of members inside the wind tunnel, and the wind can blow through without covering. And maybe also a look into the wind tunnel opens you that you calculate something what is generally not expected. So maybe if you watch here, you see these streamlines are running generally through. Yeah, of course they present this pressure on the structure what we just saw, but they neglect these fields. And for this we have to learn the program how to deal with these situations, and therefore I use this model to explain you how to cover it. And here please do following. So we developed for this type really a special surface type. We called it load transfer surface, and this is a surface would have no stiffness but only the job to suction or to collect loads and to distribute it to neighbor elements, and see how it's distributed in X and Y, whatever is controlled in this sheet. And I define it now for this type of surface. So let's go here to boundary load transfer. I define here these boundary lines. Yes, of course, you have to delete results. Maybe here's this front surface, this roof segment. Yes, back also. Oops. Load transfer here, 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 here. Yeah. Now we use these surfaces. I select it, take a rotation manipulation, say okay, please 2 times. I think the angle is 15 around this point here, and go. And now the lateral wall, the same, we have only 1 time, 45, and go. And now it's covered by a surface. Yeah, of course, looks good. Maybe only to show how this surface is working, I use maybe here the self-wet load case and say, imagine we have a wind load in X direction, standard size 1. You see, if this load is acting on this structure, this means behind, I can visualize it vice versa, that the program is distributing the surface load around these beams. No? If I say now the properties, now you see the properties is, if we open properties, they have the job to distribute it via stripes in X and Y. If I say please distribute it only in X, okay, and the program is distributing this load only right and left, and this is more or less what I want to have. Yeah. Where I say yes, of course. Now let's check coordinate system. X, X, X is everything running horizontally, so we say to all surfaces, surface edit into X. And now we have a good feeling, and if we send it into the wind tunnel, so let's say wind tunnel, open it, everything works as expected, and you see you should get this structure here and everything super, no? You say okay, now it's covered, and if you mesh it like before, today I press really often on this meshing command. Yeah, process is starting. Of course, it will create, we have a big wind tunnel now, it will create more meshes, but for me it's important that you see this, that you really have it in front of you, what means this when you don't take care about. Still, settings are really rough, so it's only made for presentations. So you have to calculate this type of structure with much more finer mesh. You have to make a mesh convergence study that you see at which mesh size the result remains the same. But what is important now, you see still here fine, going bigger, but if we show surface mesh, you see we have here such ribs, and this is really strange because my model have no ribs, but or the outer hull of my model have no ribs. And if you watch the model, you see in detail this surface is in the center, and the maybe if we have a top view in Z direction, of course these cross sections have an overstand, and so the meshes only bind around. Yeah, so if you have here this, is this right? See, and now you see, yeah, of course this simplification is working, but this is not the real structure what you want to calculate. No? And therefore I recommend following. We have a option made in RFEM. here in the mesh settings of Wind that you can only calculate visible objects. Yeah? This means if you check here, for example, please make visible all surface with the type load transfer, for example, we have only these surfaces active. And if we run now the analysis, so I do it now with this global command, that you see also this two-stage analysis, and we can check later the results. You see at first the program is doing the RWIND job, what maybe meshing and calculating the CFD analysis according to the calculation parameters what we defined. And then you have automatically a second calculation step. So if I click on it, it's the static analysis of the wind pressures from the wind analysis. You get also here the convergence diagram for the analysis, what is done, visualized here. Clear, I defined the mesh setting so rough that I can receive results pretty quickly, but here you see how the residual pressure still oscillating, in begin really big during the different iterations, and in the beginning it have a let's say a convergencing gradient, but it's still too big. And this static analysis job is still waiting for the results what are coming from the wind analysis. No? So now the first calculation job, the CFD analysis, is ended. The loads are transferred from the outer hull to the structural elements, and the program can do static analysis. Everything is fine. We get the screen back. Now the question appears what we see. At the moment, nothing. Why? Because our, let's say, only these transfer surfaces are active, so I break the visibility mode and now maybe make a wireframe model to see more. You see we get now first view what I always do, what makes my deflection, and I would say fine. Yeah, so deflection is running in wind. The next view what I do is maybe check forces. I see, okay, in the back we have tension. Oh, now also we have here tension, so it means uplifting wind. And we get also here bending moment, we see pressure is acting, and if we check now the corresponding wind simulation, you see we get also wind pressures now not only on members and on these surfaces. If you check this let's say pressures around, you see we can slice this blind. Now we have also pressure in front of this structure. Yeah. So now it seems better than this starting model. Yeah. Of course we can take a look in wind tunnel how it looks like, but for me it seems now okay, we send in something what is more real, so we covered it. We have also about these ribs, let's check it, but let's go to our wind, and you see, okay, now if I say this is simulation, show computational mesh, you see the ribs are gone, so it's more clear. So of course it's simplified, so the simplification effect is here, but you can control it like I showed you. You have in front a pressure, here a suction, so so far clear. We have this wind flow now not through the model, then we have it around the model. Of course, you can animate it. It makes really impressive graphics where you can see how the flow is going around this structure. And of course, all other results, maybe like pressure around, is similar like in RFEM. Yeah. So let's say you see you get now the pressures on these distribution surfaces, and these distribution surfaces gives this pressure to the structure itself. So let's take a look on static analysis, and you see here distribution of loads. What is here important? You have here 1D elements where you see, okay, concentrated force. This is maybe in X. We get only, this is in local X, so in member longitudinal direction, so almost 0. In Y direction, you see maybe the outer suction is on the beam, and in wind direction, you see, okay, how the wind is pressing against the vertical axis of the beam. And these forces are coming from the distribution surface and used for the static calculation to calculate these deflections. Now, this should show you how you can do from RFEM, or can use a RFEM model in wind tunnel and receive back the forces. Of course, the forces depend on what you send in and which calculation parameters you used. It's your game now to say, I have maybe here more load cases. Imagine you have maybe CFD, wind load mean, wind load gust, wind load storm, so you can define different wind schemes to apply it on the load case. To apply for every wind scheme one load case, and to apply it to the structure for further calculation. This is also possible. If you imagine you have now these 2 load cases or more, the program allows you to say, of course, I want to have a combination surf weight with wind. If you have to consider some safety factors, maybe from standard we would have 1.5. If you have some more safety factors for according any uncertainties from the CFD analysis, you can change this factor here and you can calculate, and the program is combining surf weight with wind loads in one load case. And these wind load cases could be considered. Now we have surf weight plus wind plus additional safety. You can consider this load case in any design to make a check according Eurocode, whatever. So this brings me now to the end of my demo webinar, and I want to sum up everything what we did today and give you outlook. I talked today a lot about discretization. So I showed you how you can move member elements into the wind tunnel. I showed you how you can consider surface element in the wind tunnel, and corresponding to all these effects what I mentioned to you, you can also consider surface elements and solid elements. Further, we talked about how you can consider member wireframe models in the wind tunnel, which issues appears, and how you can, let's say, close member structure wireframe models, member grids with such load transfer surfaces to distribute loads on members. And finally, I showed you how you can combine these load cases, how you receive the loads in RFEM, and how you can combine it with other loads. To the outlook, of course, our team is still working hard on these programs. We're working on several topics. One main topic is a result combination for wind loads. So if you imagine So I showed you here this distribution of loads, where you see, okay, this is maybe the forces in Z. This is acting for only one load case, but if you imagine you have here maybe a wind load case in X, in Y, in copy in X, Y, or maybe let's describe it with 0 degree, with 90 degree, with 45. So or maybe with strong and weak wind, you can set up a list of load cases you wish to consider, and if you combine it later in a result combination, maybe that you say, please make me an analysis of all these load cases. You don't receive these results here, only internal forces, support forces, but this distribution of loads is not done. So our team is just working that you get also a result combination, envelope forces, load distribution. Then we're working on a, let's say, wind statistics. This means, as mentioned, you can send in weak wind, strong wind, different wind schemes on your structure in different angles. And you also, let's say, receive here then a set of min and max values, and you can connect it with a factor how often they appear during time. And here we just working on a integration that you get something like a statistic envelope about max and min values from different wind actions, that you can calculate from this characteristic calculation value to a design value. Later, or parallel, we're working on a, as you see, what I showed you in, where's my mouse? With these surfaces here. We place these surfaces now in the center. What is, of course, one solution, but a better solution would be to make something like a hull where it describes the real surface of such a model. So I would say the surface should run around on the outer side. With this, we're working on a new surface type where you can describe the outer hull of a building, and this outer hull should directly learn to transfer loads to the neighbor elements. And this is, we call it internally wind surface, but this is also a topic where we're just working hard on it. And with this, I come to the end and give back.
Thank you, Andreas, for this nice presentation. Some words from my side, a hint. Just book your free online appointments, such as a product demonstration of RFEM 6, RSTAP 9, RWIND 2, R Section 1, or to our add-ons. Just click on that link at the bottom here, or you can scan the QR code. You can download the PowerPoint slides in a PDF format from our website. In the next days, you will get an email with a link to the page with the recording, PowerPoint, and the model of today's webinar. Okay, that's also all from my side. Thank you for your attention. Thanks to Andreas Niemeyer for his presentation. I hope we meet each other in a future webinar. Thank you again. Bye-bye.